All right. Good morning, everyone. This is GEO 319 lecture on May Day, May 1st, 2020. And it's our final lecture. So we've made it to the end of classes. So I'm going to share my screen here. And pop up our plan for today. So Andrew and I thought we would do a course wrap up today. So we were going to tentatively take about 20 minutes each to, oh, I see I've got something wrong here. Tentatively take about 20 minutes each to wrap up course. There's an office hour Monday at 11. The link is here.
That's my office hour.
Yep. So our final exam is scheduled for Thursday, May 7th from 10 to 12, 10:10 to 12:10. We are going to have the final exam at the normal time. Final exam. Andrew, did you go over the format of the final exam already?
Yeah, I mean, I didn't go into much detail, but basically said it would be, a mix of quantitative and qualitative, some short answer, and, the midterm would be a good guide, and it would be cumulative, but weighted towards the second half of the semester.
And that we would, like, details on that we would deliver, we will be on Zoom from 10 to 12 that day. We'll give you guys the test at 10, make it available. And then typically I allow some extra time past 12 for turn-in in case somebody has problems with turning it in. Does that seem, are you agreeable to that, Andrew?
Yeah, certainly.
So we'll make it due by 12:30.
And one of the reasons to allow a little extra time is that, given that it's electronic and there may be some problem solving that you would perhaps want to do by hand. We don't expect you to, again, take the time to type all that in, to write formulas and equations. So you can just, take a picture or scan anything that you have written and submit it to us electronically that way. But, that always can take a couple extra minutes. And so let us know if you have questions about mechanics of doing an exam like this via Moodle. We'll be there on Thursday and available for those questions.
Yeah. My preference is that everyone turn in a single PDF file that allows us to actually annotate it quite easily and grade and give you guys feedback. So figuring out how you take pictures and add them to PDF would be useful. For my hydrogeology class, I have everyone turn in a single PDF. Everyone was able to do that by taking pictures and collating everything into a single file, and it worked well. So single PDF would be the preferred turn-in. Okay. Any questions on the exam? Okay. Oh yeah, go ahead.
I said no.
Oh, okay. Never mind then. All right. So we do have a link to fill out evaluations. It's a quick survey. The link is here. We will post these slides after lecture, and the link should be live, so you can just click on it. I'll also send the link in as a discussion off of Moodle. So we're going to hope to give you guys some time to post these evaluations at the end of class. Okay, so that's sort of the outline, and if no one else has any questions, I'll get started with a bit of lecture here. Okay, so I'm not sure who all is in Missoula today, but it's a gorgeous day in Missoula. And if we were in class, I would take you all for a little walk down to the Clark Fork and go look at some formations there. But since we're doing things virtually, I thought I'd take us to Glacier National Park. And this picture was taken from top of, well, not quite the top, but on the going to the Sun Road near Rogers Pass. So does anybody know what formations of rock make up the majority of Glacier, of the mountains in Glacier?
You broke up a little bit there, Peyton, so you might want to repeat the question.
Okay, so does anybody know what the rock formations are that make up the majority of the mountains in Glacier National Park? Okay, so you're going to learn something today then. All right, so Glacier is predominantly made up of the belt supergroup rocks. And this belt supergroup was deposited somewhere around 1.5 billion years ago at sort of the end of the Precambrian era. It's called the Proterozoic. All right. So these rocks were deposited in a time before life had really colonized the Earth and before complex organisms were around. So during the belt, there is unicellular life, but there isn't any complex organisms. And I wanted to have us take a trip back in time and sort of contemplate what the Earth's surface might have looked like before there was any life or any vegetation on the planet. So I want you to sort of go back or take your mind and think about what the Earth must have looked like at this time. What kind of formations, what did the Earth's surface look like? What shape did it take? So I've got a few examples in my mind. So here is a close-up of some of the belt rocks in Glacier. This is the Grinnell Formation, and you see these sort of really cool banded colored formations. We think the belt was deposited in a shallow sort of marine environment. And at that time, because there was no plants, the landscape would have looked completely different. So I've got just a few pictures here to help me sort of visualize what the world might have looked like back then. So this is a picture taken from the center of Australia in the outback near Lake Eyre. And this is about one of the images I have that is the most devoid of vegetation, and probably looks somewhat like what the belt, what the situation looked like for deposition of the belt. We see a lot of mud cracks in the belt that are filled with various different kinds of sediment. We think things were deposited in really flat, channel-less areas. All right, so nothing, no vegetation to coalesce and create channelization. Another image I have that sort of might invoke us to think something like what the world looked like before the belt is the racetrack in Death Valley. All right, so this is a big playa or dry lake in Death Valley. There is some vegetation up on the hill slopes here, but in general, Death Valley is a really good place to look at sedimentology without a huge influence of vegetation and organisms. Okay, so this trip back in time allows us to think, or at least conceptualize a bit of what the world looked like before plants colonized the land and before life, ecology, and geology started evolving together. All right, so let's now take a trip downslope to where we are in the vegetated world. And we can think about how the landscape looks now that plants and ecosystems have evolved. And we see a much different picture now. We have the interaction between ecology and hydrology and sedimentology controlling the shape of our landscape. So a much different picture. So for the past roughly 1.5 billion years, essentially the Phanerozoic era, life and the earth have been co-evolving together. And they have worked together to completely change the way that the earth's surface works and the way that mass and energy are distributed around the earth's surface. Okay, so this is a picture of the Gibbon River in Yellowstone, where I did my dissertation work. And it's just upstream of the Norris Campground, just upstream of the Norris Geyser Basin. So when you look at this picture, what kinds of processes can you guys see in this picture?
It looks like there's a little bit of overland flooding, especially in the foreground of the picture. You can see that the water is not just confined to the channel.
Okay, great. So we have water flowing on the surface. Absolutely. That's basically, that water flowing on the surface is basically what my dissertation was about. Anything else you guys observe here? What other things are going on in this picture that you can see?
Looks like there's some new trees growing in the background.
Yeah, what do you think happened there so that there has to be new trees growing?
Could have been, did you say this was in the park? Maybe it could have been a forest fire.
Yeah, right. So we have a big fire scar here. All right. And there's a bunch of downed, let me just tell you, I spent a lot of time hiking through this kind of area. It's just covered in downed dead timber like this. Just absolutely about anywhere from 3 to 10 feet thick of downed lodgepole logs, and then regen, these small trees growing in between. All right, so we got fire, we have ecological succession. Absolutely. What else can we see here?
it looks like a really flat, like I think we can say something about where the stream has been in the last, I don't know, long time, because it's left this, we can kind of tell that it's probably been snaking through this little valley to make it so flat.
Yeah, fantastic. Really gorgeous floodplain here, right? Super flat. The river's been snaking back and forth across this floodplain, and we see a distinct shape of the valley because of that, right? It's got this flat floodplain, terraces of hills moving up on the valley on either side. So very distinct morphological signature for sure. What about the ecology? I see a really sharp break here, lodgepole pines. And then when I move out onto the floodplain, grasses, right? So really distinct changes in the ecology. All right, so what we see now when we move onto the landscape are these really tightly coupled sets of processes where we have ecology and disturbance, all right, fire, and hydrology and sediment transport all working together to shape the landscape and to control how energy and water move across the landscape. So a lot of this class was about looking at this set of interacting systems. So here's a picture, again from Yellowstone, of a sinkhole. And it's a great shot of the critical zone, all right? And what you see here is vegetation, and then the vegetation grading down towards intact bedrock. And we see roots and fungi that are interacting with earth materials. We can see soil moisture, all right, moving water through the system. So this zone was focused here on the critical zone, this zone where life and earth interact, and they're connected by hydrology, all right? And we talked about forms of chemical weathering where you might make things like this sinkhole by dissolving minerals, rocks and minerals, and physical weathering or the transport of sediment. You can see loose sediment that's being moved here, all right? So we have this set of interacting systems. So here's a picture taken from the Daly River in Northern Australia. And here you can see this really highly coupled set of systems. So we've got on the banks here, these are large springs. So we were studying this river to understand how much groundwater was coming into the river. And because of the underlying geology, you have this set of huge springs that are discharging into the Daly. The Daly gains almost double in size over the reach we were studying. So you see all this surface water here at the surface. This is groundwater discharge. It's feeding sets of riparian and groundwater dependent vegetation. And that vegetation is controlling the shape of the banks in these rivers. So Andrew has a great image right now of the Clark Fork and flood. And right now the Clark Fork's running at about, on the staff gauge, it's at about 7 feet, just a little over 7 feet, just above Missoula. During low water, the Clark Fork is around, let's say, 1 to 2 feet on the staff gauge. So right now it's, 2 to 3 times higher than on the staff gauge, or we've seen about 2 to 3 times the level increase in the river. All right, the Daly River, this is at low flow during the dry. During the wet, the Daly runs about 100 times higher on the staff gauge. So when you go and look at a staff gauge on the daily, you actually start, they have a series of nested staff gauges that move continually up the basin. So the river increases in flow unbelievably and much, much higher than what we might see in a Northern Rockies river. But these groundwater dependent ecosystems are able to exist even during these huge floods because they're continually fed throughout the year, even during the dry, by these springs. Right? So we get these really complicated interactions. That groundwater then feeds these vegetation. It changes the size of sediment that this kind of reach can hold onto, and therefore changes the form and the transport properties of the reach. So really complicated interacting systems. And these systems create feedbacks. All right, so one of the things that we talked about in class is how all these systems work together to create feedbacks. So here's a river, a reach up on the northern, on the North Fork of the Flathead, right near the Canadian border. And what you can see here is a horizon line, all right? And much like in Yellowstone, we have a fire scar here. So we have a bunch of older dead trees and regenerating young trees. If you look closely, there's a sedimentology break here. So this top 10 feet here is alluvial gravels, much like what you see down here. So big cobbles, river terrace. It's sitting on fine clays here. And what's happened is that groundwater recharge is soaking through these gravels, pooling on this shale layer, and now running over the banks, and we get this long line of spring discharge, all right, coming out. Well, that groundwater is now carrying fine-grained sediment. It's allowing the banks here to be less stable, and you see lots of mass wasting or more sediment transport, all right? The groundwater recharge has probably, I could hypothesize, increased since this fire, as we now have less regen or less large trees intercepting precipitation and evapotranspiring it. Right, so we get these really complicated feedbacks and connections between these systems. And they control where and when life and what types of life might exist. So here we are, here's a spring in Yellowstone. Here's another spring out in, again, in the outback of Australia. This is in the discharge zone of the Great Artesian Basin, and much of the landscape looks like that previous picture I showed you, just really dry, no water at all. And then you come upon these large springs that are fed from huge groundwater systems. But you're in the middle of the desert, you have this oasis, you get vegetation around it, you precipitate different minerals, and you get these large spring mounds. So in the distance, you can see a spring mound. So where the springs are actually raised above the level of the rest of the land surface, because the vegetation and the precipitates from the spring increase the durability of the sediments, and they don't get eroded by the wind. And so these springs all sit on high areas, and they're changing the shape of the landscape and the ecology. So really interesting sets of feedbacks between the water, the vegetation, and the weathering that change our landscape. And these feedbacks can be really nonlinear and dynamic. So here is a picture of the Great Fountain Geyser in Yellowstone. And a geyser is a great example of a nonlinear feedback. You've got this sort of constant heat flow, a fairly constant groundwater flow, but the heat and the groundwater, so the energy and the groundwater interact in such a way that you get these really nonlinear pulses or explosive times of spring discharge, whereas the rest of the time, the spring looks much like this, where it's very placid and just flowing at a constant rate. So one of the things that we tried to hit on is that these feedbacks create these really interesting sets of processes that shape our landscape. So we have this really complicated system now that we live on, where ecology, geology, hydrology, and meteorology are all working together to shape our landscape. And they feed back together in such a way that they create these incredibly complex processes and patterns. And so a big focus of this class is how do we try to take these really complicated settings and make some sense of it. So this picture is taken from the East River, north of Crested Butte, Colorado, where the Department of Energy is funding a very large project to look at trying to understand the critical zone and the interactions between all these different processes. And you can think about this like something like an accelerator or a large user facility, but now for understanding the critical zone. And the DOE is putting lots of money into instrumenting and understanding the interactions between all these systems. So here on the east, it's a great place. We can see the floodplain, like Wendell talked about, where the river has been moving back and forth and actively maintaining this flat zone. We can see the terraced hill slopes moving up from the floodplain. We can see wonderful changes. The south-facing slope here, the south-facing slope, non-vegetated. The north-facing slope, full of aspen and spruce stands. So aspect and energy balance are completely controlling where and when and how much vegetation can grow. That vegetation in turn controls the rate and type of weathering and the amount of sediment transport and type of sediment transport. So we get these really complicated systems. So what do we do? How do we go about trying to understand how these systems interact? Well, a lot of this class has been trying to think about these as systems, all right? And in systems thinking. And in systems thinking, we try to break apart this complicated set of interacting processes and reservoirs into conceptual diagrams of reservoirs and fluxes and think about their interactions. All right, so what I hoped to do in the first part of this was just set the stage that this class was about thinking about how these complicated set of processes and systems interact. And then Andrew will talk more about the fundamental tools we used to make sense of the critical zone. So I'm going to stop my share, Andrew, and then you could share your screen. Does that sound good?
Yep, that sounds perfect. All right. Thanks, Peyton. So as some of you may have seen, I posted the link to the course evaluation in the chat. And, you know, it's obviously a little different than how we normally do things. So this is a Qualtrics survey, which you'll do online. That will go to our department administrator, and she will collate the results and get those back to us soon. So apologies, I'm struggling with allergies this morning, so this is part of the curse of nice spring weather for me. But I'll do my best not to sniffle while I'm talking here. All right, so it's a rather large challenge to recap a semester-long course in a one short class period, especially when we're dividing it. So I am not going to actually go through most of the slides that I have here. These are posted on Moodle, and these are meant to be just, as it says here, a summary of some of the key things and important kind of takeaways that we hope that you all get from both Peyton and I's treatment of the course content this semester, and that you'll take with you to either upper division classes or courses, or just thinking about landscapes as you move through them. So instead of going through each of these, I will go through the slides kind of slowly as reminders of some of the things that we've tried to thread through, whether we're talking about fluxes of water or fluxes of sediment, which are the two main fluxes that we think about in this class, but we also might bring in nutrients and heat and other elements that we're trying to conserve, and that provides a basis for how we think about landscapes. I'm going to go down and kind of present a vignette of what I think is kind of an interesting way to think about Earth surface processes and the critical zone, and how it connects to the Anthropocene and human activities in some unexpected ways. And for that, I'm going to be focusing on the sediment side of fluxes on the Earth's surface. And this is, obviously something that I think about a lot as a geomorphologist. I think about connectivity laterally and longitudinally in the critical zone, and to some extent vertically, in this context of sediment, and using this framework of thinking about how are either natural or human activities changing fluxes of sediment, and what's the upshot of that? How does that affect the amount of sediment coming in from hill slopes, moving through rivers out to the ocean? And change in storage is a term that describes the change in the landscape and in the topography in relation to these changes in fluxes. So a lot of sediment is sand. It's all over the Earth's surface, of course. Yet paradoxically, we are running out of sand. And this is something that has started to sort of come into the news more and be written about more in the last decade or so, because it's this crazy paradox. On the one hand, deserts, coasts, rivers, soils are full of sand. It's all over the Earth's surface. And it's all over the Earth's surface because of weathering. It is a primary product of weathering. And both mechanical and chemical weathering by the suite of processes that we've talked about. And we use a lot of it. So what do you think our first most consumed natural resource is, if sand is the second? Any guesses?
Water.
Water, exactly. All right. So thinking about this in a mass balance or sediment budget framework, we are taking 50 billion tons of sand and gravel out of the Earth's surface. So that is a change in storage to use primarily for construction. So this says sand and gravel, but most of it is actually sand. So on the one hand, we can think about this from a mass balance framework. When we are causing this change in storage, there's going to be a topographic change and a set of feedbacks and an adjustment. But let's talk a little more about the drivers of this. This fully ties into our discussion of the Anthropocene and of the growth in urban areas. So the shift of a huge demand of sand for construction. So sand is used to make concrete. So we need that for buildings, roads, and other infrastructure. But that's not the only reason we're using massive amounts of sand. Another is that as population grows, we try to create land. Look at that. So I'm going to switch my screen share over to the time lapse, and we're going to look at a couple quick examples. So the first of these is Singapore. So Singapore is one of the largest users of sand for such a small area. It's had the most land reclamation in the last 40 years. All right, so I'm going to slow this down a little bit so we can see it. And we'll let it play through a couple times. And it's subtle when you're looking at it. You have to look at specific areas to see addition of land area because of land reclamation. But when you go back to the beginning of this frame, 1984, you can see that it is quite a bit smaller in aggregate. So this is dredging sand out of river deltas, out of the ocean, and moving it to build up new land. Let's look at another example. And that is in Dubai, in the United Arab Emirates. As you go to this landscape, you immediately see that there is a lot of sand around in this landscape, in the desert. And they have been both using it for construction. They have the world's tallest building in Dubai, but also to build new land off the coast with these palm tree shapes. So they're using sand for that. One of the crazy paradoxes about the world's demand for sand is that we have a demand for a specific type of sand. So even in a landscape like this, where there's deserts all around, this is not the right type of sand. We will talk about that in the next slide. But the United Arab Emirates imports sand from Australia. All right, let's go back to the PowerPoint. Okay, so there are massive environmental costs to this demand for sand because a lot of it is dredged from nearshore environments in the ocean. So coral reefs and marine habitat are damaged, a lot of damage to coastal wetlands. And then mining of sand and gravel from rivers is a huge industry around the world. And when you remove mass from an area, that area will adjust. So when rivers have sand and gravel extracted from their beds or from their floodplains, they incise. And that creates a whole set of issues, whether that is destabilization of bridge piers, disconnection from groundwater, lowering of groundwater tables, disconnections of rivers and floodplains, and habitat problems. So in many parts of the world, gravel mining from rivers is starting to be regulated, but that means that the sand extraction is moving to places like these massive industrial dredging operations in ocean areas, and also in delta areas. So for example, the Mekong Delta in Vietnam is a place that I think you looked at in the virtual field trip that is sinking for a variety of reasons, one of which is sand extraction. And sand extraction occurs either through these large-scale industrial type dredger outfits, or all the way down to small-scale dredging of river sand from a river bar. So all scales all around the world. Okay. There's a lot of it, but because of the way that sand weathers, we mostly, for construction uses, want sand that has been moved by water. And this is a close-up, so a 50 times magnification and a 2,500 times magnification. And here we can see fluvial sand, either washed and unwashed, and here we see aeolian dune sand. And it's a little bit subtle, but the bottom line here is that aeolian wind-blown transported sand is more rounded than waterborne sand. Waterborne sand is a bit more angular, which means that when it's crushed up and used for concrete, we want the waterborne sand. The other reason that we tend to want waterborne sand from beaches is that it has a whiter color because of the chemistry of it, the minerals that are present in terms of how it's weathered. So in terms of building white sandy beaches and resorts off the coast of Dubai, we want nice white beach sand. Okay, so the weathering processes, whether it's the resulting shape or the chemistry of that sand, is connected to how we satisfy our demand for sand. This is a great podcast that's linked down here about these issues. And one of the vignettes in that podcast is a case where an entire beach in Jamaica disappeared. It was stolen by sand thieves. And through forensic sedimentology, they found the sand at another beach in Jamaica where a resort had wanted more nice white beach sand. Okay. Sand ties into geopolitics. China is building up new islands by dredging sand from the sea and building islands to establish control over the South China Sea. And then finally, bringing this around to what we are all concerned about now, this sand shortage, because of our demand for it, is going to affect our ability to produce a billion or billions of vaccines. Vaccines need glass vials, and glass is made from sand. There's no good alternative to sand because things, plastic vials tend to leach. So we need glass vials for vaccine, but because of our use of sand, there's a shortage of it. So among the many uncertainties about how COVID-19 and the current situation is going to play out, one of them is sand. So this brings us around to the idea that we live in the critical zone. Surface processes affect us, and our use of surface processes, whether those are sustainable or not, have in many cases unexpected sort of feedbacks and interconnectivity. And I hope that we have sort of emphasized this idea of the critical zone and the interconnections here and how those are connected to geological, biological, biogeochemical processes in the critical zones, sometimes in obvious ways, sometimes in not obvious ways. So I'm going to leave off on that point. My slides are posted, and we have a few extra minutes where Peyton and I are happy to stay on and answer questions and chat, whether it's about today's content or otherwise. In terms of the course evaluation, we do want your feedback. Once you start that survey, you have, I think, a week to actually get it submitted, but it doesn't take long, so you might as well just do it all in one sitting. So thank you, everyone, and we will, like I said, stick around here for a few minutes and be available to talk with you, throughout the next week in terms of getting ready for the exam and otherwise. So I will mute myself, and I'm going to switch my screen share back over to Google Earth Engine so we can look at time lapses as we answer questions and chat more if you would like.
I guess I have a question about this time lapse right here. Why are they making the palm tree shaped sandbars?
Tourist attraction.
Oh,
So they're building resorts out on these palm tree shaped sand new land. So, this is not so much a situation where they need to build new land because they are running out of space to satisfy the new population. They could certainly go inland, but it's a visually appealing and interesting way of trying to build attention around the world. Whereas in a place like Singapore or other places around the world, Lagos, Nigeria is one of the world's mega cities. They are building new land off the coast there so that the millions and millions of people living there have somewhere to go. There are places along the coast of China, same thing, these mega cities where they're building new land just to allow space for people. That's not the case here.
is that new land that they're like building in mega cities? Like, I guess my question is it safe? Like, is it safe to put infrastructure on sand that they're depositing themselves?
That's a great question. And I guess the answer is it depends. So one example of land reclamation and building new land that is a little bit older is in the San Francisco Bay Area. So parts of San Francisco are built on sand and mud that was dredged from the San Francisco Bay Delta to allow the city to expand. And during the last big earthquake in 1989, those were the areas that had the greatest damage because the way that the ground shook in those areas caused the buildings to be destabilized more there. So in some cases, no, it's not necessarily safe. It depends on, partly on how the sand reclamation is done. It also depends on things like, the hydroclimatic and tectonic setting, which you could say about, many human uses of the environment. How safe is a coal ash pond next to a coal mine? Well, it probably depends whether there are going to be hurricanes or earthquakes there or not.
Okay, yeah, thank you.
Easy to get mesmerized by these Google Earth Engine images. And the one about Lagos building out its coastline is not as clear in this this time lapse, and I'm not even sure that this took us to quite the right place, but Lagos is an example one of the examples that I read about in terms of land reclamation from sand. All right, well, Peyton, you want to go ahead and end the recording, and if people want to